Okay, the Karim, question about the quiz or about the lecture?
No, not a question. Can I just join through my computer, like leave for like 3 seconds?
Yes.
To join my.
Sure. Bismillahirrahmanirrahim. And today's lecture, we're going to continue talking about the topics that the special cases of node-faulted method. So if you recall, in the previous lecture, we spent so much time on node-faulted method and the techniques that we're going to use in node-faulted method. So just a reminder about homework one is posted and due Thursday, 11:59 p.m. And for quiz 2, inshallah, will be next Wednesday. It will be something similar to, hopefully similar to, based on the response that's, based on your performance, it will be something similar to quiz 1. The coverage, however, will be chapter 3 and chapter 4 until section 4.4, which includes only the mesh, not the mesh, the node-faulted method. Okay. If you recall in the previous lecture, we introduced, actually, we deep dove into node-faulted method, and we started with the general case, then we moved to special cases. We saw that for node-faulted method, we are introducing new intermediate variables, which are the node voltage, the essential node voltage, rather than solving directly for the current. So we're going to use those essential nodes voltages, those essential node voltages to solve for the branch current. We also introduced discussed and solve problems on node-faulted method when we have a dependent source, and we saw that if we have a dependent source, the situation is exactly the same. The only difference here is that you have extra equation to account for. And we started with the special cases. The first special case was a trivial one. We have a voltage source between two essential nodes, and this fact, having a voltage source between two essential nodes, will actually reduce the number of unknowns. Now let's continue talking about the second thing, or the second special case is let's discuss what happens also in some cases. If you see here, we have a situation where we have a voltage source between two essential nodes. So this one is an essential node. If we set the reference node, this one is also essential node. The fact that we have a voltage source between two essential nodes actually simplifies the calculations here. But here we have more than one. So we have another voltage source between, so let me use different color here. We have another one here between two essential nodes. So what should we do? We have multiple options. The first one is actually to write the node equations as they are. So starting with node 1, we know the voltage at node 1. So node 1, V1, we know V1 equals to 50. Then moving to node 2, V2 minus V1 divided by 5, V2 divided by 50 plus the current of this voltage source. So we don't know the current of this voltage. Remember, we're trying to apply. This is the current that's flowing from node 2 to node 1. This is the current that's flowing from node 2 to the ground. And this one is the current that's flowing from node 2 to node 3. Now we apply KCL also at node 3. So we have, the first one is the current that flows from node 3 to the ground. Then we have, why I have plus minus, okay. So this one should be okay, minus I. Then I have the current that's actually flowing, the current of the current source. So you see here, I have two unknowns, usually, like I have two node voltages with two unknown voltage, but I have a voltage source, a dependent voltage source, or between two essential nodes. The problem with this dependent voltage source, or with this voltage source in general, is the fact that we don't know the current, because remember, this is an ideal voltage source, so it doesn't, it maintain constant voltage no matter what the current is. So if we substitute, if we add these two equations, equation 1 with equation 2, you'll end up with the following node equation. So you know V1, the only thing missing is V2 and V3. Then you can go ahead and try to solve it, but the solution is rather complicated in this case. So you need to make a substitution, then go back, try to find a relation between V2 and V1, etc. So it's going to take a while. So it's not an efficient way of solving circuits. And remember, in this chapter, we're concerned about fast and efficient way of solving circuits. So what we're going to do, we're going to create some sort of a supernode here. So we're creating a supernode here. So let's imagine that. Okay, let me keep it here. So I lump all of these two nodes here and combine them to form a bigger node. So a supernode is a node, is a big node where it contains two essential nodes connected by a voltage source. So let's see what happens. So we're going to treat this one as a single node. So if we apply a node voltage method, here we have standard way of applying node voltage method, V2 minus V1, which is 50 in this case, divided by 5, plus V2, which is the current that's going through the 50 ohm, divided by 50, plus V3 divided by 100, minus 4 equals to 0. So is it clear what we did? Is it clear, Shabab, what we did?
Yes.
Okay, very good. So we treat everything here as a bigger node. So in this case, if we simplify it, we will end up with 0.22 volts to V2 plus 0.0 of V3 equals to 4. This is the first equation. So now I need the second equation that relates V2 with V1 and with V3. So it turns out that going back to the original circuit here, going back to the original circuit, if we apply KCL here, okay, fine. If we apply KVL here, I will get the following. So if I start from this point, find KVL, and returning back to this point, I will have the following. Apply KVL, I will get minus V2 minus 10 I phi plus V3 equals to 0. Or V2 equals to V3 minus 10 I phi. So this is the second equation. So I have two equations, three unknowns. The I phi is due to the fact that we have a dependent source. If we have an independent source, we will not have I phi. So now the problem is similar to the case of node voltage method with dependent source. So all what I need to do now is express the find the expression of I phi in terms of V1, V2, and V3. So I phi is this current. So IV will be V2 minus V1 divided by 5. In this case, I can write it like this, minus V1 plus V2 minus 5 IV equals to 0, and this is the third equation. So I have three equations, three unknowns. V1 is known here, V1 is 50 volts. Can I solve it? The answer is yes, because I can construct a matrix and then invert the matrix, and you can do it using your calculator. And if I solve for it, I will get V2 equals to 60 volts, V3 equals to 80 volts, IV equals to 2 amperes. Is this clear, Shabab? So let me summarize what we did. So we had, this is a very interesting example because it covers two special cases. So we have two voltage sources, and these two voltage sources are connecting two essential nodes. So the fact that one of them is connecting one essential node to the ground simplifies the value, reduce the number of needed equations. So instead of in general here, you would need three equations with three unknowns. So now it's two equations with two unknowns. But we have another voltage source that connects also two essential nodes. So in order to solve for this circuit, we might end up doing a lot of substitutions. But it turns out there is a fast and efficient technique of solving for a circuit by lumping the two essential nodes that are separated by a voltage source and constructing a big or huge node that captures these two nodes. And this is known as the supernode. So if you apply the supernode, if you apply node voltage method on the supernode, we're doing exactly what we're doing with the standard or standard node voltage method. The only difference here is that in the equations, we are considering the current flowing in this direction as contributed as related to V2, current flowing in this direction is related to V2. However, current flowing in this direction and that direction is related to V3. So we construct the equations. This is the first equation. The second equation is we know for sure, and this is how we construct the supernode. We know for sure that the two essential nodes that are contributed to the supernode are separated by a voltage source. So by knowing the voltage in one of them, you can know the voltage in the other. It's just like a shift. The difference between them is 10 multiplied by IP, and that's what we did, and that's how we found equation 2. We had to do an extra step because we have a dependent voltage source, and we want to actually derive the equation of the dependent, or the constraint equation of the dependent voltage source. Then we can construct the solution as standard way. So any question?
Yes, sir.
Yes.
The supernode, can I choose any two nodes to make them a supernode?
The supernode, any what?
Any nodes to make them a supernode?
What do you mean?
Like, for example, can I make node 1 and 2 supernodes? Like one and
It's not going to be useful. The only difference here is the reason for making supernode, because we don't know the current. If you tell me the current passing through this voltage source here, then I don't need a supernode. I cannot apply Ohm's law to find this current. So remember what we're doing here, we're applying Ohm's law to find the current that's flowing through the 5 ohm resistor, or the 50 ohm resistor, or the 100 ohm resistor. Okay, good. Okay, let's do an exercise here. So we need to use the node voltage method to find V naught and the power delivered by the 2 ampere source. So we have this circuit. This one should be exercise 1. We have this circuit, and we want to find the current that we want to find V naught and the voltage and the power dissipated, or the power delivered by the current source. So if we try to solve it, we can see that we have a voltage source between 2 essential nodes. So I can set this one as my reference node. I have the first node here and the second essential node here. So this V1, this one is V2. However, I have a voltage source between them. So in this case, I can actually use either of the special cases, but it's always better to use the essential the supernode concept here. So if I use the supernode concept here, I will get this supernode here. This is the supernode, and they need to apply the node voltage method. So the number of essential nodes is 3, and we have so applying KCL, we get 2 plus V1 divided by 50 plus V2 divided by 150 plus V2 divided by 20 plus 55 equals to 0. So if I simplify it, I will get V1 equals to 25 plus V2. Oh, no. So if I simplify it, I will get 1 over 50 V1 plus 1 over 150 plus 1 over 175 V2 equals to minus 2, and this is the first equation. So now I found the first equation. Now the second equation is relating to V1 and V2, because remember V1 and V2 are related, or there's a difference between them. There's a voltage source between them. So applying KVL, I will get minus V1 plus 25 plus V2. Remember, V2 is from here to the ground, V1 from here to the ground, equals to 0. So in this case, I will get V1 minus V2 equals to 25. And this is the second equation. So I have 2 equations, 2 unknowns. I can easily solve for it. by inverting the matrix. So V1 is minus 37.5 volt. And remember, V1 is actually what? It's V0, right? V2 is minus 62.5 volt. And the power of the 2 ohm source is going to be using the passive sign convention. So the power should be, we should choose the positive sign here. But however, V is negative, which is 37.5 multiplied by the current, which is 2. And this is going to give me minus 75 watts. And that current source is actually delivering power to the circuit. Is it clear, Shabab? Okay. Okay, very good. So now let's solve the last exercise for today's lecture, and we're going to. This is one of the interesting exercises. It says that we used to have, or we should try to use the node voltage method to find V1 in the following circuit. However, the issue here is that not all the cases the super node will be our best option. Because here, see the problem, this voltage source connects, the dependent voltage source connects 2 nodes that are not adjacent to one another. And this might complicate the problem itself. So this one, so this one is a sober node. So I have this node, of which I know the voltage. I have this node, and I have this node. So basically, I have 4 essential nodes, 3 equations, 3 nodes, but one of them is connected to a voltage source, which is going to give me a 60 volt source, 60 volt voltage here. So using the sober node, the problem will become more complicated. You want to prove that, just try to solve it with sober node. Since I know the voltage across one of these nodes. So remember what we did when we talked about sober nodes. Actually, the situation we have is especially here. So I don't know the voltage here, so I'm trying to find the current at this point. But in this case, if I try to find the current, I cannot apply Ohm's law because a voltage source can take any current. So what I need to do is actually to solve it in a smarter way by noticing that V2, which is this one. So V2 is actually applying KVL. It's going to be 60 plus 6 IV. Or I can write it this way, V2 minus 6 IV equals to 60. So this is the first equation. Now I need to apply the node voltage method here at V1. So this one is straightforward, V1 minus 60. This is not a super node, this is just a standard node. Divided by 2 plus V1 divided by 24 plus V1 minus 60 plus 6 IV divided by 3 equals to 0. So what is this one? This is actually, let me write it here, this is V2 from this definition. So V1 minus V2 divided by. Okay, so now if I simplify the equation, so we'll end up with 1 over 2 plus 1 over 24 plus 1 over 3 V1 plus 0 V2 minus 2. I wrote 0 V2 just for simplicity, I can ignore it, equals to 50. So this is the first equation. So this is the second equation. So I have V1, V2, and V3. I can leverage the fact that I know V2. I can leverage the fact that I can relate easily V2 to IV. So I eliminate the need for knowing V2 here. So now let's try to find IV. IV will be V2 minus V1, which is 60 plus 6 IV minus V1 divided by 3. And if I simplify it, I will end up with so I have 3 equations, 3 unknowns. I can easily solve for V1 and V2, V1, V2, and V3, V1, V2, and IV. But I'm not asked to find V2, I'm asked to find V1. So if I solve for it, I will get V1 equals to 48 volts. IV will be minus 400. Is it clear, Shabab? Okay, any question? So this exercise, the last one, is just to show you that yes, in most cases, the supernode will be like a good choice. But remember here, if you're applying node voltage method, you're trying to solve for KCL. So if you cannot find an expression for the current in terms of the voltage, you cannot relate the current to the voltage, to the node voltage, then probably this is not your best bet here. So you should look for an alternative here. So since here we know that we have a 60 volt source, so the 60 volt source can take any value, any current, depending on the circuit itself. So we cannot actually, there is no one-to-one relation between the 60 volt source and its current. So it all depends on the circuit. And this is due to the fact that we have ideal voltage source. So it turns out that we have to look for an alternative to solve for the circuit. But this kind of problems is kind of like is rather complicated compared to a standard problem that we saw so far. So any questions, Siobhan? Okay, with this we conclude today's lecture. My recommendation to all of you is to spend this weekend trying to solve exercises on node voltage method. You can find as many in the internet. You can find a lot of exercises. I will try to upload some exercises from the book. And try to be familiar with this, and also try to. I posted some of the tips and guidelines of how to solve this system of equation using your calculator. So in the exam, if you just write until this point, then do all of the calculations on your calculator. This should be enough. Ahmed?
Doctor, is studying from the slides and solving book questions, and are them enough for the midterm exams? And
first of all, you need to study. Everyone, please pay attention here. So when you choose the textbook, we usually choose the basis that the textbook is easy for you to follow. So the textbook is your first reference, is your main reference. We're basically covering everything from the textbook. So you see, all of my exercises are from the textbook. I'm not bringing any exercise outside the textbook. So the textbook should be your reference. The slides will be your kind of like guidelines. Okay, we covered this. If this is your first introduction, so this is my suggestion. When you study it on a daily basis, you refer to my slides and textbook. When you if you run out of time, then the slides should be okay for it. But again, your reference should be the textbook, not the slide. Yasser?
Victor, can you please as well upload some problems on chapter 3 with the
Yes, I did.
You did?
I did 30 minutes before the class. You will see them be
Yeah, I did not see that. Thank you.
الله يعطيكم العافية شباب. See you inshallah next week. Enjoy your weekend. By the way, the midterm date has been set, and it's going to be July 8th. Yes, Abdullah.
For Gradescope, can I take another picture? I won't do anything to the paper, just a better picture. Is that fine? Or do I have to use the same one I sent to WhatsApp?
No, you can use different picture, but you should not do anything anything related to adding or writing things on that.
Oh yes, of course.
It has to be the same papers. Aziz?
Yes, doctor. Do you have enough hour after this class?
No.
Okay. Can I contact you through email?
Yes.
Okay.
We'll see you, inshallah, Shabab. I need to run for a meeting, so we'll see you, inshallah, next week.